Welcome to this lecture. So, in this lecture, I am going to talk about Stark effect and perturbation theory. How perturbation theory help us to study the Stark effect. So, the objective in this problem is study the effect of an external weak electric field which is directed along positive z-axis, that is, electric field is basically represented like this, and it is acting on the ground state of, say, hydrogen atom. So using this, our aim is to approximate the value of polarizability of hydrogen atom, right? So this is our aim. So first of all, let us talk about that. What is Stark effect? Stark effect is shifting and splitting of spectral lines of atoms. Atoms and molecules due to the presence of external static electric field. So this is the meaning of Stark effect, right? So that means if there is a single line when no field is zero, no field is there, but when field has some finite value, then this line may split. So such type of possibilities comes under the effect under the name of Stark effect. So let us try to do a little algebra to understand and to try to calculate the polarizability for the hydrogen atom. So let us start as follows. So in the absence of electric field, so when no field is there, that means it is a unperturbed system. Hamiltonian is written as of hydrogen atom, and we are writing hydrogen atom, Hamiltonian for hydrogen atom in CGS units, and this Hamiltonian for hydrogen atom is given as this H naught is equal to P square by 2m minus E square by R. Now the Eigen function of this Hamiltonian is given as this R theta phi NLM. It can be written as psi NLM R theta and phi. So we can split it into radial and the angular part. So it is theta and phi. This is general representation. Now when electric field is on, when electric field turned on, the interaction between atom and field generates a term, means it gives rise to the additional term, and let me call that as HP, and it is E epsilon Z, right, because it is acting along that direction. Now let us try to calculate the energy, and energy up to second order perturbation is given as E100, E100 naught. This is 100 Z. This is from standard perturbation theory. Right. So, but as we know that the value of this part is equal to this integral, and the value of this integral will be 0, and you can assume that it is a standard result. So that means the shift is in the energy is only because of this parameter, and let me call it as energy shift, means second term is contributing for the energy shift. So that means this energy shift is written as like this, or we can say that this energy is equal to E100 naught plus delta E, because this term will be 0. At smart square, it is equal to E100 minus ENLM0. In terms of this energy shift, let us define the polarizability. This polarizability can be defined in terms of this energy shift, and it can be written as minus 2 delta E upon epsilon square. So let me try to put all these values here. It is 2, 1 over epsilon square is this factor, and the value of delta E will be E square epsilon square, and summation so this epsilon square will cancel out with it, so it is minus 2 E square summation now. Let us try to calculate E1 or ENLM or E2, whatever, because LM are 0. So because first of all I want to calculate the denominator, so E10 is equivalent to E1 and E200 is equivalent to E2. Now as I know that En is equal to minus E square by 2A naught 1 over N square. This is the standard relation from the problem of hydrogen atom. So from here I can write down E1 is equal to minus E square by 2A naught, and E2 is equal to minus E square by 2A naught and 1 by 4. So that means let me do one thing, that E100 minus ENLM, it must be less than equal to E100 minus E200, or we can say that they are nearly equal. So it is E square by 2A naught, because minus sign will be there, so it is minus and minus 1 by 4. So that means if I simplify it, then it will become minus 3 E square by 8A naught. Right. So this is one thing regarding this denominator. Now let us try to calculate this numerator. So if I substitute this value here, then the alpha will become less than equal to 16 by 3A naught. Because I have substituted the value of this here. Let me go back. Let us do one thing. Okay. Not to do this, but yeah. So alpha is equal to or less than equal to minus 2e square is there. It is NLM Z and 100 its mod square over minus 3e square over 8a naught and summation over NLM, right? So that means I can say that it is alpha is less than equal to 16 by a naught by 3 summation NLM is not equal to 100 NLM Z and 100. Now I have to calculate this value, that what is its value. So for this, let us proceed as follows. Let me recall this, right? NLM, and to calculate its value I will use a very wonderful trick of or wonderful property of completeness of the wave function. So let me call it as, because if I consider NLM is equal to 100, then that value will be 0. So let me call it as it is for all NLM. It is can be written as like this. That's whole mod square now it's equal to let me expand this, because it's a mod square, then it can be written as NLM Z100 and it is 100 Z and NLM. This can be expanded in this way, because psi mod square is equal to psi star, so it is sitting like this, right? For all NLM, it's equal to, let me rewrite it this first and this towards that side, so it is 100 Z NLM right. And if I put summation over this, this goes to here, because this part is also constant, this is also constant. So in that manner I can say that it is 100 Z and summation over it so it is a completeness condition and its value is 1. So if its value is 1, so that means now it will be equal to this. Okay, one Z is here and another Z is here, so I can write down it is Z square over 100, but its value is nothing. This is from again from the problem of hydrogen atom. You can say that its value is a naught square. That's right. So that means alpha can be written as 16 by 3 a naught into a naught square, so it is 16 by 3 a naught cube. So that means it is its approximate value, right? So as I know that 16 by 3 is 5.33 a naught, right? And similarly, but if I try to look at the exact value is 9 by 2 a naught cube, so that means our value, this value agrees with it with certain error, right? Because 9.2 is 4.5 and 16 by 3 is 5.33, so that means in this way we can calculate or we can estimate the polarizability for the Stark effect, right? And it agrees with the actual value. If I improve our approximation, means if I incorporate higher order terms, then things can be improved better, right? So this is a way that how perturbation theory is used to explain the Stark effect, try to calculate the energy shift, and once energy shift is there, then we can calculate the polarizability. So energy shift can also be calculated from here. So this energy shift is basically E square epsilon square NLM over this. So if I use their values here, then we can say that, so it is E square epsilon square, and the value of this is equal to, this part is A naught square, and the value of the denominator will be minus 3 E square eight A naught. So it is E square epsilon square with negative sign 8 A naught over 3 E square. Negative I have incorporated here, and it will be, yeah, it can be substituted. This A naught square will remain as it is. So this will cancel out. Let me again go back. Yeah, am I right? So that means it is epsilon square, or I can say that minus 8 epsilon square A naught cube by 3. So this is the value of energy shift which we are getting on the application of applied electric field, right? So energy will be changed on the application of the electric field, right? So that's all for the Stark effect. Thanks for watching this lecture.